Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. In the previous 4 lectures, we have discussed the LTI system, the convolution, the aperiodic non-convergent response or aperiodic non-convergent signals, impulse response and step response. Okay. Right now we are discussing the continuous time signals and the impulse signals that we are used to represent all those continuous time signals. In this lecture, we are going to understand the stability and causality of LTI system, and the upcoming next lecture, we are going to discuss the difference equation. Okay. Now, first of all, we have to understand that what we are talking here, we are talking about a LTI system. Now, first 3 lecture we discussed the convolution, we discussed the discrete time signal. In the 4th lecture, we discussed the continuous time signal. All these signals are all fed to the system, which is a LTI system, linear time invariant causal system. Without that specific condition, we can't cope with the signals. We can cope with the convolution sum. So to consider LTI, to consider the convolution sum, we need a LTI system and vice versa. Okay, so we'll continue with 2-3 examples, and we will conclude this lecture by understanding stability and causality of a linear time invariant system. Okay, so let's begin. Okay, so as in the previous lecture we have discussed this specific example. Okay, and the next example we are going to take is example is this one. Okay, so now if you consider the signal, the signal is saying that this is a function, x function of t, which is equal to 1 when the value of t is in between 0 to t, and otherwise it will providing the value provided a non-zero value. And the next we have found that the impulse signal or impulse response is also provide us with a value t, where the condition here, the value of t need to be in between 0 to 2t, where we will find a non-zero value, and other than that we will find a zero value element. To understand this specific problem, if you just go through this specific problem, that the same process has been taken here, the same process will be taken care of. Okay, now it has been, the result of this specific example is 0 for t less than 0, half t square for 0 to t, block letter t into small t minus half block t square, block letter t, capital T, and the value of small t should be in between capital T and small twice of capital T, and the value in case of this function, the value of small t should be in between twice of capital T to thrice of capital T, and also it will be 0 after the value of thrice of capital T. And this specific example that I have that it has been shared in this book. In the previous lecture, we have discussed the similar kind of a signal, where we have taken care of all the mathematical process which is needed to understand the output signal of this specific input signal and this specific impulse response. Okay, so this is the mathematical representation. Okay, so this is the x tau. Okay, this is the ht minus tau. This is the ht minus tau for 0. This is the range in between the signals are varying. The impulse response the range of the impulse response is varying. The waveform, the important part is the waveform is preserved, because we already know this is a linear system, so the waveform will not get polluted or corrupted, but the system will be get delayed or advanced depending upon the range in which it has been calculated. Okay, these are the different ranges, and we have multiplied this specific each ranges with the input signal, and depending upon that we get the output value. Okay, and this is the output value that we talk about. We just multiplied this each and every form, and we get after adding add up all the signals, we get this value. Okay. So now if we take another example that has a broad spectrum here. Okay, we are going to understand this specific then we go to the properties of the linear time varying system. Okay, so this is the another example. The example is saying that input signal that has been provided us with the value e to the power 2t into u to the this is the input signal. Okay, what is that? X of t is equal to e to the power 2t into u into minus t, and h of t is the impulse response, which is equal to ut minus 3. Okay, so it is a little bit problematic. We will going to elaborately discuss this specific problem. Okay, so if we go along with it, then what we have here, the first we will realize the input signals, the impulse responses, then we will understand the range of the specific signal. Okay, first we have to understand this is the negative unit step response. This function is a negative unit step response. So how, as it is a negative unit step response, how the graphical representation will be? It will be in this way. Okay, why? Now put the value 1 in place of t. What we will find? What we will find? U minus 1, u minus 2, u minus 3, u minus 4. So for any value where the value of t is greater than 0, we will find the 0, right? No non-zero elements will be found when we put the value of t as a positive. If we put t is equal to plus 1, plus 2, plus 3, when we put those values, we will find u function of minus 1, u function of minus 2, u function of minus 3. So we are not going to find any non-zero elements, right? All the elements will find at the right side of the signal is 0. Now instead of using 1, 2, 3, suppose just use, instead of 1 we use minus 1, minus 2, minus 3. What we will find? What we will find? We will find a value which is a non-zero element. Suppose you put in place of t minus 1, what we will have? We have u function of 1. So now u function of 1, we have already several times we have discussed what is a step signal is. Okay, so we know that step signal is a stream of impulse signals where the value of step signal will be 1 when the value of n is greater than 0. So if this value is greater than 0, we will find or greater than equal to 0, we will find a value, we will find a non-zero value. Simple, we will find a value 1. So when we put minus 1, okay, or 0, you will find a value. So that's why this graphical representation is shown in this way. The value of 0 we will find 1. Okay, now when we put t is equal to minus 1, minus 2, minus 3, we will find u function of 1, u function of 2, u function of 3. So all the step response, the stream of step response that we found is a non-zero element. Now that non-zero element will be multiplied with e to the power 2t, whereas the t, the value of t, okay, the value of t will be minus 1, minus 2, minus 3. Okay, so it could be represented as an exponential function, but a decremental negative exponential function. That's why this input signal has been represented here in this process. Okay, from this is the highest value, from that the value of the signal will be decremental. Okay, now take the impulse response. This is the impulse response. Okay, u function of t minus 3, right? So what this step function provided us, that when we put the value t is equal to 1, 2, 3, we will not find any value. Okay, now put the value 4, okay, 5, 6, 7, 8, we will find the value, right? It means that step response, or sorry, this is the impulse response. The impulse function will be look like this. It will be start from t is equal to 3. Okay, t is equal to 3. Now in this picture, what we have here, we have seen that the value has been started from t is equal to minus 3. Why it has happened? Because the u function of t minus 3 will usually, it should start from t is equal to 3 at that, from that point. Okay, it means it should be here and it should start from here. Okay, right? It is a straight value. The stream will be should in this region, but what we have done, we have just taken a mirror image of the specific signal. Okay, so what we have done, h of t we put in place of t a minus t. For that minus t value, the signal has just reversed. It just take the mirror image of that specific, the origin, it is just nothing but the mirror image of the original signal. That's why the signal has been started from the same t is equal to minus 3. Okay, if you take a close look, it has been started from t is equal to minus 3. Okay, from this region it goes through that region, from this to this. So this is the impulse response. Now depending, now suppose t is equal to 0, at t is, this signal is started from t is equal to 0, but t is equal to 0, the tau is basically minus 3, so it has been started from here. Now when we taking h of minus t, you have to put t, tau is equal to minus 3 to get a non-zero element. So at t is equal to 0, this signal has been started from t is equal to minus 3. Okay, and the signal will be in this range. Okay, so this is the impulse response, this is the input signal. We have already got what we need to know, or all the resources that we are required to perform the convolution operation. Okay, so now when we multiply this and this, we will find this specific output. So these are the graphical representation of input signal, the impulse response, and this is the graphical representation of the output signal. Okay, so now we are going to discuss the mathematical representation by which we will conclude how the output signal has been extracted from these two specific resources of input signal and the impulse response that has been provided. Okay, so now if we start with how the whole operation took place, it could be understandable very easily that this is the first of all, we know this is the input signal. Okay, so what we have done, this function, okay, sorry, now, okay, this is the input signal. So what we have done here, the signal x tau and the ht minus tau, the plotted as function of tau in figure this. We first observe that these two signals have regions of non-zero overlap regardless of the value of t, right? The signal has been started here, input signal, the impulse has been started from here. Okay, so this point, when they overlap, we will have a non-zero value, right? When they don't overlap, we will not find any non-zero element. We don't find any non-zero element. But in this case, in this example, this specific example, we have overlapping of the input signal and the impulse response. So by when we multiply both of them with each other, we will find a non-zero element. It's an easy conclusion we can draw, right? So now if we proceed with that specific understanding, what we have here, that when t is equal to now the condition for impulse response, now it has been considering here. We are considering the condition of the impulse response. Now what is that? Is that when t is equal to t minus 3 is less than equal to 0, the product of x tau and xt minus tau is non-zero, right? The value of t minus 3 should be less than equal to 0. Other than that, we cannot have any value. That's why we have taken the consideration, the value of t should be, or the value of tau should be 3. Okay, without that we cannot realize this function, the function that has been given here as the impulse response, which is step function u function of t minus 3. So the value of t minus 3 need to be less than equal to 0. Okay, to what, to make this h t minus tau function as a non-zero element. Okay, not this function. That's the basic. That's why it's a problematic for to understand. This is the first understand. This is the impulse response. We have reversed the specific impulse response. So now, if we are talking about this, it needs to be greater than 0, right? T minus 3 need to be greater than 0, but that's not the function we are talking about. When we are operating on the input signal, we have reversed the impulse response. So that impulse response will provide a different function. That function is known as h function of t minus tau. So for that signal to be non-zero, we need to have the condition where the t minus 3 should be less than equal to 0. When it is when the t minus 3 is less than equal to 0, what will happen? The value of t will be less than equal to 3. Okay, that's the product we need to understand here. Okay, but we are not going to do that. What we have done, when t minus 3 less than equal to 0, the product of x tau and x t minus tau is non-zero. For what? For the value of tau should be in between minus infinity to t minus 3. Okay. Yes. Okay. So what we have done, we have provided us with the convolution sum is that y function of t is equal to integration of minus into t minus 3, where the e to the power 2 tau into d tau is the function, and after integrating we will get half e to the power 2 t minus 3 tau. Okay, for t minus 3 greater than equal to 0, the product of x tau is 0 non-zero, for which value? For tau is minus infinity to 0. Okay, when the t minus 3 is greater than equal to 0, if suppose t minus 3 is greater than equal to 0, what will it provide us? It will provide us the value of t is greater than equal to 3, right? The value of t is greater than equal to 3. For that specific purpose, we will have a non-zero product of x tau and h t minus tau when the value of tau is in between minus infinity to 0, so that the convolution integral will be x tau is equal to minus infinity to 0 e to the power 2 tau d tau, which is equal to half. Resulting of yt is plotted as this figure. Okay. As these examples and those present in section 2.1 illustrate, the graphical interpretation of continuous time in discrete time convolution is of considerable value in visualizing the evaluation of convolution integrals and sums. It is as clear as that. The same process has been taken here, that when now we have taken two considerations. One, the t minus 3 is less than equal to 0. For that reason, the value of t should be less than equal to 3. Okay. And for t minus 3 greater than equal to 0, the same process, the t is greater than equal to 3. Okay. Okay. So this is the mathematical representation that we have provided with. So we will conclude the convolution sum here now, and we are going to start with the properties of linear time invariant system. Okay. So the properties that we have already discussed, all the properties of linear time invariant system, and if we just revised it all, that what we get, that first we get that y function of n, the discrete time signal, is in between minus infinity to plus infinity, which is x of k into h of n minus k, and it could be written as this, xn multiplied h of n. The same process will be followed in case of continuous time signal, where the convolution integral of convolution integral will be represented or mathematically represented using this format. Right? So as you have pointed out, the one consequence of this representation is that the characteristics of an LTI system are completely determined by its impulse response. It is important to emphasize that this property holds in general only for LTI system. In particular, as illustrated in the following example, the unit impulse response of a nonlinear system does not completely characterize the behavior of the system. So it's an important point to note down, is that as in the following example, the unit impulse response of a nonlinear system does not completely characterize the behavior of the system. So that's why we have taken a linear time invariant system. Now if we consider a non-linear time invariant system, what we have? First, this is the constant discrete time system with the unit impulse h of n is equal to 1, otherwise the value will be 0. For n is equal to 0 or 1, h of n is equal to 1. Okay, if the system is LTI, then equation 2 completely determine its input output behavior, in particular by substituting equation 2.41. So the equation is this. Okay, right? We find the following explicit equation describing how the input and output of this LTI system are related. Y of n is equal to x of n plus x of n minus 1. Okay. On the other hand, there are many nonlinear systems with the same response, that given in equation 2.41. Is that this? Okay. So, and the same way we can understand the commutative property of convolution, is the x of n into h of n. It can be written as h of n into x of n. In the same process, summation of k e to the minus infinity to plus infinity, it could be written as this way, and it could be written as the same process in case of continuous time. We can write the same process. Okay. The same way, x of t into h of t can be written in the form of h of t into x of t. This expression can be verified in a straightforward manner by means of a substitution of variable in equation 2.3, 9 and 2.4. For example, in the discrete time case, if we let r is equal to n minus k or equivalently k is equal to n minus r, equation 2.39 becomes this. Okay. It could be written as this form. So this is also known as commutative property. The distributive property can be written as distributive property can be understandable is this, the xn into y h1n into h2n. If we multiply them, we will get this value. It's very much similar to the homogeneity or linearity of a system. Same process in continuous time system, we will find x of t into h of h1t plus h2t can be written as x of t into h of t, and the same process for continuous time system. And it could be realized using the block diagram that x function will be fed to this system, which is the impulse response of h1 and the h2t. That could be provided as the output yt, and this yt can be this block diagram can be rewritten or can be redrawn as the figure as this similar to this one. Okay, so if we go along with this same process, we will find this specific criterions. Okay. This is the example that we can convolute using the same process. Okay, this is the yn which has been realized here using this is the same process. This is the input signal half whole to the power n into un plus 2 to the power n into u function of minus n. Okay, and h of n is equal to u of n. If we let x of x1 n is equal to half of whole to the power n un, and x2n is equal to 2 to the power n into u to the power minus n, it follows that y of n is equal to x1n plus x2n into h of n. Distributive property of conversion, we may rewrite this as this. So fine. And y of n is can be written as this, and y1n can be written also this way. The same process, the same technique. Okay. And the associative property also showing that association means x of n into h1n into h2n can be rewritten and this format. Okay. So we can take any of this signals or impulse response or the inputs, so we can take them out and put them back again. So if we go along this way, you can find that this property is proven by a straightforward manipulation of the summation of integrals or involved examples, verifying it area and r in given problem 2.43. Okay. So it could be written as this format also. Okay. It's the same process. This is the one, and it could be written in this format. The same process we can graphically can be also be realized. The same process can be graphically realized. h1n and h2n we can write in this format, and the same process we can decompose, or we can write this block in the form of this block, and vice versa. Okay. So, and LTI system with and without memory, it's simple process. The same process that we have already discussed. What is the memoryless, and which is the system which is memory with or without memory, a memory system or memoryless system. As a system with memory, or what is the memory mean? It means basically when the output signal depends upon the past input signals or past output signals. Basically, past output signals, it will be known as a system with memory. When the system output doesn't depend upon the past output signal, it will be considered as a memoryless system. Okay. And the invertibility of a LTI system is basically nothing. Suppose we have a input signal which fed to this impulse in this system. The output of this system has been fed to another system, and we get this output. Now if this system will said to be an invertible system, when the h of n into h1n will provide the convolution of the multiplication of hn of h1 multiplication of h function of n and h suffix 1 function of n will provide us the impulse signal. It will be said that these two specific systems are invertible to each other. Okay. This is the example. Go ahead with the same process. Suppose consider LTI system with impulse response this. Using this convolution sum, we can calculate the response of this system to an arbitrary input. Okay. So this is we already know that this is the convolution sum. So since u of n minus k is 0 for n minus k less than 0 and 1 for n minus k greater than or equal to 0. You already knew that. So this equation becomes y of n minus infinity to n, because we know that this value is 0. Okay. So we will find that minus infinity to n, this value is x of k. Okay. So how this function can be considered? Now that this system which we are first encounter section is a summer of accumulator that computes the running sum of all the values of the input up to the present time. As we saw in section 1.6.2, such system is invertible and its inverse as given equation 1.99. So this equation can be written as this, and this is also known as the simply first difference equation. Okay, it's chosen as x of n del n. So we will put this h1n is equal to del of n minus del of n minus 1. Right now, h of n, if we multiply this, what will we have to do? We have to multiply the step response or step signal into del of n into minus del of n minus 1. By doing that, we will find this is del of n. Okay, so this is the difference equation, and we are going to understand the difference equation in the next lecture, and we will also understand the causality and stability of our system. So thank you.